Hello, my name is Thomas, and this is my first video for Project 3. I'm going to be doing Inviscid Flow. So first, I'm going to create my system, right-click on Geometry, New Design Modeler. Alright, now that I'm here in Design Modeler, I'm going to orient my axis, click into the XY plane, and I'm going to sketch a circle and a rectangle, both centered at the origin. The circle is going to have a diameter of 1 meter, and the square is going to have side lengths of 50 meters. So I'm just going to do a general dimension from these four corners to the axes and adjust everything down here. 1, and then these are all going to be 25. And there we go. We've got our cylinder in the center and our rectangle or square around. Now I'm going to go to Concept, Surfaces from Sketches, click into Sketch 1, Generate. Alright, now we can move on to meshing. Now it's important to note that I'm going to be using the same geometry and mesh for every single case for Inviscid, viscous laminar, and viscous turbulent, so I'm only going to show it in this first video for Inviscid. It's going to be the exact same. I'm just going to duplicate it twice, and that's going to be what I use for the laminar and turbulent cases. Okay, our meshing is ready, so we're going to click into Mesh, right-click. Oh, wait, first, no, we're going to name each side. This is going to be the inlet, this will be the top, this will be the bottom, this will be the outlet, and this will be cylinder. Okay, now that we've named all these, we can insert method. The geometry is going to be this main face. It's going to be triangles. We're going to switch the element size now to 0.18. Alright. And then right-click, insert sizing. Make sure we select this edge right here. Apply. Number of divisions. I'm going to do 1,000 divisions with a 1.1. No growth rate actually. No curvature. Hard behavior. And then I'm going to right-click, insert inflation, this geometry with this boundary. The inflation option, we're going to select first layer of thickness, and it's going to be 0.001 with 300 max layers and a growth rate of 1.1. And now we can hit generate. Okay, the meshing is now done. It took quite a while. Let's take a look at it. Alright, this looks pretty good. So the outside is a bit less fine, but the inside is very fine, and especially around the cylinder, which is exactly what we want. If you go to statistics, you have 461,082 elements, which is exactly what it said before, which is good. Alright, now we can move on to setup. First we're going to update the mesh. And now we're going to go into the setup. Double precision. I'm going to do 4 solver processes because that's what my system can handle. Okay, now we're here. Everything is loaded. First thing we're going to do is swap the model type to Inviscid. Alright, going to go to my residuals and switch them all to 1 times 10 to the negative 6. Alright, then we're going to go to Materials, Fluid, Air. I'm going to adjust this just slightly. I'm going to give it a, this is density, of 1. And we're going to go to Boundary Conditions, Inlet. The velocity is going to be 5. Alright, and now we're going to go and set our bottom and top. They by default are walls, but we're going to make them pressure outlets. And we're going to check prevent reverse flow, because we don't want that. Though it really doesn't make too big of a difference for the top and bottom, I don't think. Because the flow should be parallel to them, so it really doesn't matter one way or the other. And then the outlet, we're also going to make prevent reverse flow. This is probably the most important one, but even then it should never happen. Okay, and next we're going to adjust our reference values. Click into that, compute from inlet. You can see the velocity updated. Next we're going to go to methods, change our scheme to simple, our pressure to presto, and then we're going to go to initialization, click into it, more settings, number of iterations to 50, and initialize. Okay, we've now finished initializing, so I'm going to click into run calculation, and I'm going to put a really ridiculous number of iterations, because this one takes ages to converge to the convergence I set, but it's no big deal. I have time. Alright, just over 3,000 iterations later, and here is the residuals. As you can see, it starts to oscillate quite a bit here, and it really struggles to reach 10 to the negative 6 conversions. But it does eventually. So from this point, we are going to do some results here. I'm going to go to reports, forces, and I'm going to print the forces on the cylinder. And here you can see the coefficients, the drag coefficients. For viscous, it's 0, because Inviscid, and pressure is very close to 0, basically 0 as well. So that's exactly what we were hoping for. Also, I'm going to go to plots, XY plot, double click into it, and I'm going to plot the pressure coefficient on the cylinder. Here's what that looks like. Very nice parabola from 1 to 1 with a base of 0. That's good. I'm also going to plot the velocity magnitude versus x vector as well. And you can see it looks like a half circle. This is again exactly what we wanted. We want no velocity, basically a stagnation point at the ends of the cylinder. And we want maximum velocity, which comes out to 10, which is exactly double the input velocity, at the top. So that's good. Alright, from here we can go to our results and get everything else that we need. Alright, here we are in the results. So I'm going to add a contour map. We're going to call it velocity contour. And it's going to be on symmetry 1. The variable is going to be the velocity. We'll put 301 contours. And apply. And as you can see, here's our velocity contour. Very low velocity here, very low velocity here, and high velocity at the top and bottom. Alright, next we can do some streamline action. Let's get these in. Start from the inlet. We'll do 1,000 points. Variable velocity, good. Here are our streamlines. As you can see, they diverge from the stagnation points and they come closer together at the top and bottom, where it's faster. And the last thing we need to do is get a pressure contour in here. And that's going to have, we'll do 501 contours. Location symmetry 1. And here's our pressure contour. As you can see, very symmetrical. High pressure where the velocity is low, low pressure where the velocity is high. Very good. Okay, that's it for the Inviscid flow.